Okay. Yeah, this course is slightly different, right? Yeah. So we have. I did make one question for you guys for the example, but we are going to have the exam. I'll be putting it out in the next week sometime. So how it's going to, so homework, first of all, homework 6, correct? Homework 6, I said I changed my plan. It was made not due, but just collect the notes and submit it. Right, this was, let's make it due on April 7. Correct, that's what we agreed on, is that right?
Yeah, I think so.
And midterm 2, what did I say about midterm 2? I remember I said that we are going to have it in.
You said it's on April 9th?
Yes, no, the date is clear to me, but I remember having had this discussion that I'm going to have it during the session. It's, I think, 24 hours, I think, something like that. What was the, do you guys remember?
Yeah, you said like you're going to upload it just before this class, and then we do it during the session, I believe.
That's correct, right? So I did decide on that. So yeah, so we'll make it short, so it will be concentrate on the class notes, okay, mostly. And yeah, I know there was a discussion on what is the content that will be there, right? I think Angela, you raised that point.
Yeah.
I think I did look it up. Homeworks 5 and 6, sorry, 5 to 6, sorry, 4 to 6. So this will be topics, will be homework 4, 5, and 6. 5 and 6 is pretty much spectral relativity, and homework 4 was on action principle for the Maxwell's equations. So write the Lagrangian and how we got to that. Mostly about what is the energy in electrodynamics, what is the how magnetic field is perpendicular to the displacement, and still we can talk about energy associated with magnetic fields, correct? So that kind of stuff, and we will have it during the class hours. I'll post it a little bit before that. By little bit means very little, and just have maybe 2 to 4 questions, reasonably simple to attempt on. Okay. The exam is not expected to be very complicated, but I want to have a formal setup so that we go through the assessment. Okay, the idea is to have a formal assessment. Okay, so concentrate on problems that can be done in 15 minutes. Don't concentrate on too long problems. Does that help? I know it's a little different from the usual, so it might be a little vague, but helps from the comments I made.
Yeah, are we allowed any resources during the exam? I know you were saying that you wanted us to fix the camera on our paper and whatnot while we're going. Like,
yeah, let's not make it too much. So I will say, as you are sitting now, like have your face pointed. Like now, your face is pointed, correct? That's all. Okay. Paper is not necessary. I'll assume that if I really suspect you guys based on your eye motion and other things, I can at least suspect what is happening.
I don't think it's possible to focus on both the paper and the person.
Yeah, don't bother about that. Just keep your camera on. That's it. Okay. If by chance the internet doesn't work, you go through the exam as it is. I'll trust you guys. Okay. So we'll go with the trust. Like we are three of us. I mean, Harsha, you, Justin, and I trust all three of you guys. So we will have be honest. That's all.
Right.
Okay. I think anyway I've had a take-home exam, so just be honest, and we can. Yeah. So then the question comes: should I be allowing things or not? Yeah. How about this open book exam?
Okay.
Open book, open notes exam. So there's no problem, right? Internet, yeah, we have fixed time, so open internet exam. How about that? Okay, let me write this down so that I remember. Yeah, open book, open internet.
Then in that case, why not just have a take home? I don't understand.
Because I want an assessment. See, I like take home. Yeah, that's correct. But I really want my students to be in front of me. I mean, I can tell this openly. It's primarily because of Harsha. Okay, he's not there. I need him to be there. Right? So, yeah, I'm picking names, but still, I think I'm not comfortable about the whole situation. That's my point. Okay, so open book, open notes, and open internet. Yeah. So that we have a formal 1 hour assessment, and expect the exams to be easier than the homework. It has to be doable in 15 minutes. Correct. Okay. Reasonable? Yeah. I don't know. Maybe I'm thinking in a weird way, but I'm pretty much being frank. Okay. Okay. So let's proceed forward. I think we did reasonable amount of special relativity. But now, why we did all this? Of course, primarily because Maxwell's equation almost immediately imply relativity. But there is one nice catch in all those things. Relativity does not require, or how about this? First of all, Maxwell's equation comes up with the fact that C is equal to a constant. Right, C is equal to epsilon naught mu naught. Right, that's speed of light, and we interpret it as speed of light. But special relativity doesn't say that Maxwell's or photons are this particular are the maximum speed. It could have happened that there could have been another wave which could have been moving with constant speed, and it was photon that was relative. So that was a possibility. Or more specifically, what I mean is that there are more than one waves that go with speed of light. One is, of course, electromagnetic wave. Second example is gravitational wave. Maxwell got lucky in a sense, in many ways, that the wave that he came up with, that was exactly the one that was needed for special relativity. But if light was a gravitational wave, he wouldn't have seen that, right? So he, in a sense, slightly got lucky. I mean, it's a way of telling it. So, so special relativity is related to Maxwell's equation, but then one would expect that Maxwell's equation would be Lorentz invariant, and it should be having the transformation property of special relativity. So that means to say, how does electric field transform under Lorentz transformation? Right. So our theme was that anything that you have, any physical quantity, you want to construct a 4 vector. Right, there is an energy, and momentum constructs a 4 vector, velocity as a 4 vector form, acceleration as a 4 vector form. Where does the electric field fit in? Is that clear? So what is the electric field part? What 4 vector associates electric field? Any thoughts on it? Okay. So it turns out that electric field actually is a tensor. Right, so electric field and magnetic field together transform as a tensor, and we'll see that. But let's go slow here. So let's begin with, so this is electrodynamics in 4 vector notation, right? Oh, I should be zooming in, correct? This is readable? No, right? Probably not. But I saw some videos of the recorded ones. I think zoomed in ones are much better. Yeah, right. So electrodynamics, I mean Maxwell's equation in 4 vector form, right? So the point is that in Lorentz transformation, what is the 0th component with respect to any vector plays a big role in the Lorentz transformation. So it's nice to see what exactly they are in the electrodynamics. So let's begin with the following. We identify that there is a remember there is a 3 vector, so A, and there is a phi, right? So this is electric potential. And this is your electric scalar potential, if you want. And this is magnetic vector potential. Right? Remember, so we base it on these 2. And these 2 together form a 4 vector. Okay, that's the idea. And we will see how this all fits in. And there has to be a speed of light, right? This is energy, and vector potential has a momentum kind associated with it. So this is phi over c is the 0th component, and this is your spatial components. Remember, momentum and energy come very similar to that. That gives you a thought that, oh, electric potential has electric potential energy. If I multiply by charge, I get a potential energy. So this is energy, that's momentum. A is actually a momentum associated, or momentum per unit charge, if you want. So that's, we don't see that very clearly coming out in earlier, unless you wrote a Lagrangian for that. That's the only place where that shows. So that's the first realization, or first observation, that that's a combination. And let me raise this. And next is, let's construct a, and always remember that up and down are, this is contravariant and covariant, right? Contravariant is upstairs, or superscript, and subscripts is covariant. So a mu is equal to minus phi over c. Right. Okay, and how do you go about that? You can always start, if you want to get the subscript, you will multiply by g mu nu and then a nu. I'm just going through the details a little bit, but we don't have to. Like, this much is sufficient. I mean, I've almost constructed the whole of special relativity without really going through this metric or anything. But technically, what happens is that g mu nu is a matrix which is minus 1, 0, 0, 0, 0, 1, 1, 1, all zeros except the diagonal ones are 0. So when you multiply these two, because of this negative sign, it gives you that factor, right? So when you start from the top and come down, you get minus phi over c times vector A. So that's the details of showing this. Okay. Any is that clear what I wrote? I very quickly, hurriedly said that. Okay. So that's the idea. Typically, as far as positions go, you can either start with upstairs or the contravariant version or the, so notice it is the top one that has a positive. So we sort of make a choice there. The contravariant position vector is the positive one. In principle, you could have started with the bottom one also, but usually there is a notation there that everyone picks with. What about derivative? Maxwell's equation involves gradient and time derivatives, right? So, so we will talk about d mu, which is now a covariant vector. That means it is in the subscript, and this will be equal to d by dt, and there is a 1 over c there to take care of the dimensions, and that's a gradient vector. Okay, so that will be your two simple notation. Am I still in the view? Yes, I'm still in the view. Okay, so that's your two points one has to take care of. And now let me erase this part a little so that I get some space. Okay, so now based on that, I construct a tensor. This is upstairs or downstairs, so should be careful. Yeah, F mu nu. Oh. Yeah, so that's a contravariant vector, but now I'm constructing a covariant tensor with both downstairs. So both are in the subscript. Remember, upstairs, when you go from subscript to superscript, only the time part changes. There are two pieces. So when you go from mu, goes from subscript to superscript, the zeroth component of mu changes sign. And when nu goes from subscript to superscript, zeroth part changes sign. So this is a definition now. This will be defined as derivative of mu with nu, but I'll make this anti-symmetric. This is d nu a mu. Okay, so that's going to be your definition. So this is also called the field tensor, tensor field, if you want. Okay, so okay, so now we want to identify. This was very clear. That was definition. But what is this now? Based on this, what can we say about this? There are 16 components here. Correct. This tensor or field tensor, let me call it. So this is field tensor or tensor field. Tensor field, I think. So what are they equal to? Let me put this the following way. So there are 16 components here, but I'm going to write this in the following way. F00, so that's here. When both mu and nu are zeroth component, that's one piece there. Then there is F0i, right? Let's call it F0j. Right? That's, so if there is a 4x4 matrix here, that's your three components. F01, F02, F03. Similarly, when I go in the column format, there is Fi0. So if I keep the column the same and row changes, so that's I represents the row. And then there is a 3x3 matrix here. That's Fij. Is that clear what I did there? Right, that's a 4x4 matrix. I split it into a 3x3 matrix, a row vector, a column vector, and then there is one element separated out. Clear? Any questions on that?
Yeah, the one element you say is separated out, or it's like the F00, you're saying that's not a part of the row vector or the column vector?
Oh no, by separated, or maybe the language here, right? So what I mean here is that the 16
It's still a
components.
4x4 matrix. It's a matter of representation, right?
Yes, that's all.
I
I'm
think
I'm just describing or showing the fact that the 16 pieces has a structure like this.
Okay.
That's all. Okay. That's what I meant. Okay. And now I want to identify what these are. Right. So there is F00. What is it? F0J. What is it? Fi0. What is it? Fij. What is it? So I would like to see what they are exactly. And they will come out to be electric and magnetic field. That's the point. Okay. So with me till now? So first let's begin with F00, right? Easiest. F00 by definition is D0 A0 minus D0 A0. Right? That's the same thing. That's 0. Correct? So that's 0. Easiest, right? In fact, whenever the indices are the same, because of the antisymmetric nature of this tensor built up, tensor construction, they'll all be 0. So all the diagonal components will be 0 for this tensor. Right? The field tensor, the diagonal components are 0. Okay, F11 is 0, F222 is 0, F33 is 0. So that's F00 is 0. Okay. Let's start with next is F0J. I think I can switch the. Okay. So next let's do F0J. Right. So this is D0 AJ, right? And minus of DJ A0. Okay. Remember, D0 is time derivative, correct? That was our understanding. The 0th component of derivative is time derivative, and spatial parts are gradients. So this is equal to 1 over C d by dt. AJ is nothing but vector, right? The vector A, the vector potential. So let me write that as, I'll introduce the vector sign, and I'll keep the J also, just to clarify that that's a vector. That's a double. It's not really necessary, but just for insight in a sense, if that helps. Okay, that's your vector minus dj. That's a spatial component of the derivative. That's gradient, right? That's gradient. So again, I'll put the vector also and the j. That doesn't. That's kind of overdoing it. It could be confusing, but this is the same. J represents the same indices of the vector j. A0 is phi over c. Okay. What's the mistake I made? There is a mistake here. Or is that a mistake? Yeah, what is the mistake? Yes, what's the mistake? Check the signs.
Oh yeah, the contravariant is the positive one, right?
Yeah, because A0, this is covariant. That means to say it's in the subscript.
That's minus, right?
That should be minus exactly, but I wrote it as positive.
Okay.
Is that clear?
So then what about the
because
dou zero would also be, would it be minus as well?
no, I
Minus?
defined derivatives are defined downstairs with the positive one. That's what I clarified in the beginning. So let me tell that again. So notice, so x alpha is CT x. X alpha subscript is minus CT x. But when it comes to time component, d alpha, that is the covariant part, is the positive one. Okay, and d alpha is equal to minus 1 over c d by dt gradient. Why would you say that should be like that? Remember that d mu x nu, let's keep it different. D mu x nu has to be delta mu nu. That's how it should work out. Since you want to make this work, you always define with opposite sense. If you choose your position to be contravariant, then the derivatives has to be covariant. Okay, so in the tensor sense, both have to be coming out differently. Okay, any questions or concerns?
I don't see the connection, like, based on what you just put up there. Why does that cause an issue with the signs on what you were talking about before on the previous?
Oh, no, this is to clarify that. Oh, yeah, so the point was, so keep that in mind, and let's say come back to here. So I think, I felt Angela's question was that, okay, this should have a negative sign here because A0 is there.
Mm-hmm.
But then I interpreted Angela's concern to be that, oh, gradient with the subscript should have a negative sign also. But gradients are always, subscripts are positive when it comes to derivatives. Anyway, this is space, so this doesn't even come into picture. This is spatial part, it's always positive. So it's not directly related, but I was reminding you in that context that
I was talking about the first term, the 1 by c dou by dou t. Shouldn't that be negative was my concern, but since you cleared it, yeah.
Yeah, so now this is possible, right? One might wonder that, oh, what about this? This is in the subscript, should it be negative? But derivatives in the subscript are positive, or they're opposite to the ones in the with the position case. And position is pretty, I mean, almost all textbooks, all the popular literature are consistent that they will choose the position to be contravariant or the superscript is chosen to be the positive ones. All the popular ones.
Okay, so what you were saying before about when you're saying that you had made a mistake, then you didn't actually make a mistake? Is that what you're saying?
Oh, no, there is a mistake now here. Oh, I've not corrected it yet. So there is a negative sign here.
About that, yeah.
Yeah, negative sign there. Sorry. Yeah, okay.
Okay, so why
correct?
Like I don't see the connection. Like why, based on what you showed on the other board, why does that indicate that that should be negative?
No, it doesn't. It doesn't. This is just because whatever I said before.
Okay.
Right. This is not there. But then while I was mentioning, immediately Angela pointed out that, oh, what about?
Oh, okay. Okay.
So I said for that. Yeah. So the chain of arguments maybe is not completely there, but yeah, now it's clear. Okay.
Okay.
So, so this is seems like if I would take out a 1 over c and interpret this as dA by dt plus gradient of phi, right? And this whole thing is a vector plus a vector. So it has components, so it is the jth component of that. Agreed? What is that quantity in the brackets?
Electric field.
Electric field, correct? Remember your definition of electric field, negative of the electric field.
Yeah, that's what I was wondering. Isn't E minus grad phi plus dou A by dou T?
No, minus, both minus.
Both minus, okay.
Both minus.
Okay.
Okay. You can look it as, should we go there? Yeah, I can.
No, maybe it's just my memory is wrong, yeah.
Yeah, I think one can quickly see that, I suppose, without taking too much time. Let's do it. So remember how you go about that is that del cross E is equal to minus of d by dt of B, right? There is a magnetic field now, but magnetic field is del cross A. So that's del cross A. Right? So you say that, oh, del cross with electric field plus dA by dt is equal to 0. Right? That's what you learn from Maxwell's equation. One step, right? Just one step. But if this is true, that means that whatever this vector is, so we are telling the curl of a vector is 0. If a curl of a vector is 0, that vector can be written in terms of a gradient of something. So that means that E plus dA by dt is a gradient of some scalar function, but then you want to identify this as a potential, electric potential. Remember, electric potential energy, this is like a force. So that interpretation requires you to put a negative sign. That negative sign is not mathematically needed, right? But that is for interpretation purpose, that you can identify this as energy, that's as a force, or force per unit charge, energy per unit charge, potential. So that gives you that connection. And that's a negative. When you put it to the right hand side, that's a negative. Okay. So that's Maxwell's equation right in the forefront itself. Okay. So this is equal to minus 1 over C electric field. So this horizontal, the row vector right on the top, right? There is a 4 by 4 matrix we're talking about. The 4, oh, did I write it somewhere else?
It doesn't say suggestion you adjust the camera to.
Yes, I'm sorry. It's hard to follow it. Yeah. I get carried away. So I just wrote, I identified this to be the electric field, and then I wrote minus 1 over C electric field, right? That's all I wrote. And then I was comparing it with this 4 by 4 matrix. So we have found that this is 0. That's the electric field. Like they will sit as zeros. I'll write it explicitly at the end. So this is 0, E1, EX, EY, EZ, right? That's the 3 components of your electric field in the first row of that matrix. Agreed?
Yeah.
Good? Okay.
Can you say that one more time, please?
Yeah, so let me go to this side. So F mu nu, forget that piece is there. Okay, so what we have discovered is that this is a 4 by 4 matrix. This is 0. F01 is nothing but minus 1 over C E1, the first component of the electric field. The next piece is minus 1 over C E2. And the next one is minus 1 over C E3. Right? That's your 4 components of the first row. And this is we are interested in finding this whole matrix. Is it clear? The F mu nu construction here, can you still see that in the word? No, right? This is antisymmetric. That means to say that if I were to flip mu nu, it changes sign here. Is that clear?
You're saying they'll sum together?
All together. Okay, so let me go back to 5 and prove it. Okay. So F mu nu. So F nu mu, I defined F mu nu, right? Instead, I'm going to evaluate F nu mu. I'm going to reverse it. So that's the same as d nu a mu minus d mu a nu, right? Rewrite this as, take out a minus sign out and write this as d mu a nu. Basically, I wrote this term first, that term second, right? Minus of that. So that's minus of F mu nu. Good. So that means to say that if I have found F01, I have got F10 also. Agreed? So these two are antisymmetric. So this must be plus 1 over C E1. That must be 1 over C E2. And that's plus 1 over C E3. With me? We also said that because of the same antisymmetry, whenever mu and nu are identical, that's all 0. So this is 0. That's 0. And that's 0. We found a lot of them now, right? Out of 16, we have found how many? 3, 6 plus 4, 10, right? 6 remaining. Not 6 remaining, it's only 3, right? Because if I find these three get determined because of antisymmetry. And what we'll see is that there will be magnetic field sitting here in a very weird way, but in an antisymmetric manner, they'll be sitting there. That's what is going to happen. Okay. Any questions at this stage? Right. So I defined mu, and then I constructed a so-called second rank tensor using these fields. Okay. So now let me go and let's see. Yeah, let's. We want to do Fij, right? So let me pick a new. We are done with the 0 component, so let's do Fij. Remember, whenever I use Latin index, they're running from 1 to 3. Right? Whenever I use Greek index, it runs from 0, 1, 2, 3. So this is all spatial now, 1, 2, 3, 1, 2, 3. So this is a 3 by 3 matrix. Is that clear? So this is the same as di. So this gradient comes in here times Aj minus of dj ai. Correct? And okay. So let's actually evaluate this. Okay. So let's do F0. So this piece will be F02, right? F02, this piece here. That's equal to D0.
Are we on Greek index or Latin index?
Oh, sorry. F12, right? Oh, I'm sorry. 1, 2. Yeah.
Not,
There's no Greek here. Sorry. Yeah, my bad. Completely. Okay, sorry to confuse. 1, 2. So that was this piece, right? I was in the second row.
Mhm.
So that's F1, 2. So that's D1 A2 minus of D2 A1. Okay. And remember your cross product, right? Somehow that seems like there is a 1, 2, 2, 1 cross product comes in this form. But let's keep this like that. And let me write F1, 3 now. So that's the same as, what will this be? So D1 A3 minus D3 A1. And same thing, F2, 3 will be equal to D2 A3 minus D3 A2. Okay. What does it look like? Maybe that's not ringing a bell completely. So let's actually think of del cross A, right? So remember, B is equal to del cross A, correct? And let's try to see if there is any comparison in there, right? What is the first component of B? Let's how do you do this? So BI here, right? BI is equal to epsilon I JK, or maybe K, I should write K I J, and then there is gradient of I and A of J. Agreed? So B1 would be equal to, am I still in the, yeah, still in the board. B1 is epsilon 1. Once it is, I have occupied this, the other one has to be 2, 3 or 3, 2. Right? 2, 3 or 3, 2. I mean, there are various ways of looking at this. I'm just doing it this way. That's +1 del 2 A3. And this is minus sign, so that's minus del 3 A2. And that's the same as what shows up as F2, 3, correct? These two are identical. So that means to say that this one can be identified as magnetic field, the first component of the magnetic field, B1. Clear? Let's keep, I cannot write another line, right? So maybe one more line I can write. B2, similarly, will be epsilon 2. It has to be 1, 3 or 3, 1. So 1, 3 del 1 A3 plus epsilon 2, 3, 1 del 3 A1. No more. Okay. Yeah, not bad. So that's what is 2, 1, 3. That is a negative sign, correct? So that's minus of del 1 A3, and this is positive sign. Okay, all old features. But this one is not the same as F1, 3, except that it's off by a sign. Can you see it simultaneously on the board? Probably not, right? Because I'm barely seeing it on my screen. Can you guys see this equation on your?
Yeah, a little bit. Like it's just like the top part of it's cut off, but you can still see it.
Just, okay. So so if you had to look at it, so here, okay. But then you'll get that cut off. So this one comes out to be equal to minus B2. And it doesn't matter when you're doing spatial part, it doesn't matter upstairs or downstairs. Okay. And if you identify this equal to Clear? So if I were to go back into the, oh yeah, it's still visible, right? This matrix that we were building, that's actually B3 here minus B2 and B1. Okay. And since it is antisymmetric, I can fill the rest in. This is minus B3 plus B2 minus B1. Okay. That's your field tensor. So electric and magnetic field are not vectors. Okay, we always say that it's a vector. What does that mean? We always say it's a vector field, right? And now I suddenly say that it's not a vector, it's a tensor, right? It's part of a tensor. So does that mean that earlier it is wrong? That when we say that electric field is a vector?
A vector
So there's
is
a small
actually a tensor as well, right? Of different rank,
different.
particular rank.
A vector is a tensor or a
Oh,
vector
yeah.
is a tensor of rank 1. Okay, but
Okay.
now we are saying electric field is part of a tensor of rank 2, right? Second rank tensor.
Okay.
So what went wrong, or what is the difference? The point is, whenever we say a vector, there has to be a transformation associated with it. So usually, until you reach special relativity, whenever we say vector, we never specify vector under which transformation. It's always about rotations, right? An electric field is a vector with respect to rotations. But electric field is part of a tensor with respect to Lorentz transformation. Is that clear? It's still a vector under rotations. But it's part of a tensor. It's not even a tensor. It's part of a tensor when it comes to Lorentz transformation. And magnetic field also is part of a tensor as it sits here when it comes to Lorentz transformation. Clear? Where else do you see this structure, like magnetic field is sitting inside this tensor in a very special form, right? B1 is sitting this way, minus B2, B3. You see it somewhere else also, similar structure. A rotation matrix, which will be just 3 by 3, will also have the structure. Okay, if you were to talk about rotations about an axis, that also is antisymmetric, a Coriolis for example, that will also have that structure, but that's just for your information. We won't invoke that here. Okay, so the main idea is we introduced two things at this point. Let me write that together. So let me make some space. So what we have here is, oops. Right, we have a mu involves the vector potential and scalar potential, and the field, so that's a vector, right? Vector potential and scalar potential is part of a 4 vector, that's a mu. But electric field and magnetic field is part of a second rank field tensor, and that we showed is minus 1 over C E1 minus 1 over C E2 minus 1 over C E3, right? And since it is antisymmetric, it has this structure. Like, that's pretty much observation. I didn't do anything significant. Okay, that's all. So that's an observation if you want that this can be written as a fourth rank or second rank field tensor, and this is a first rank tensor or a vector, 4 vector. This is a 4 tensor. Clear? Yep. So that's good. So now we have identified electric potential and electric fields. We also need currents, right? Or let's see. Let me see it. What's the next step? I should say. I want to go in the right path. Yeah. Yeah. So let's actually, now we want to build Maxwell's equation, right? So Maxwell's equations are 4 Maxwell's equation. So how does Maxwell's equation look like here? But for that, we need one more piece, right? There is Maxwell's equation also involves current and charge density, charge and current density, charge density and current density. Right. We have the electric field, magnetic field, time derivatives and gradients are here, and electric potentials and vector potentials are there. One more piece there is charge density and current density. To see that, let's keep this as it is. Instead, let's process a set of equations that I provide. So let's do. So let us do the following. So d mu, let's calculate what is d mu f mu nu. Okay. Notice mu is summed up. That means that it has to be you have to use the index notations. Okay, and that is also the feature. Oh, before I proceed, I think I would like to do it this way. Yeah, let's me introduce one more thing. Okay, let me go back and let me do one small thing here. Oops. Once I have f mu nu, I can also write f superscript mu nu, right? Okay. How would you do superscript mu nu? Remember that whenever one of the component switches place, you change the sign for the time component alone, not with space components. Okay. So if I were to change mu, that means I will be going downstairs. So this will change sign. This will change sign because that will involve nu alone going around, but this will not change sign because this is all space, pure space. This has part time. One of the component is time in this. One of the component is time in this, and this is both times. That should not change sign, but that is 0 anyway. Is that clear how I argued it? So this will be equal to 0 plus 1 over C E1 plus 1 over C E2 plus 1 over C E3. And when I write the index here, it doesn't matter because these are actual vectors in rotational sense. So these are it doesn't matter whether it
Would it be correct in saying it's just minus f downstairs mu nu?
No. So you're suggesting, you're trying to say f mu nu.
Oh, the B component will remain the same, is it?
Okay. Can you read this?
Yeah, yeah.
So f mu nu will be equal to, if I go 1 down, so this will be equal to f mu nu. I cannot write this, right? How do I explain? Okay, use g mu nu. So then it will clarify. F mu nu is equal to f g nu alpha times f mu alpha. nu has to be there. Okay. And this has a -1 sign whenever alpha is 0. So this will be equal to whenever alpha runs, right? Alpha runs from 0, 1, 2, 3. Whenever alpha is 0, the 0, 0 component has a -1 there. So this will be, let me put this way. F mu 0 is equal to minus F mu 0. Yeah, I think that's the way to say it here. And F 0 nu, if you want, is equal to minus F 0 nu. Helps. And if I were to put both downstairs, that becomes plus, because I have switched 2 times, right? Each switch involves a negative sign. Did I clarify? Was that your question? No. Angela?
Yeah, kind of.
Kind of, okay. Ask me again, try asking again.
I was just asking, so is your F mu nu going to be minus F mu nu in the downstairs, like subscript?
No, right? Because the space part doesn't change at all.
Won't change. Okay, yeah, I get it now. Yeah.
Right, so it won't be. Yeah, it's only the time parts change. Anything that has a time component that
Yep, I
changes.
get it.
Yeah. So this is -1 over C E1. But it's just an organization. We're not talking about Maxwell's equation. The physics is in the Maxwell's equation. This is just we are seeing that where does it fit in the Lorentz frame, Lorentz transformation. That's all we are seeing. So this is 0, and this remains the same. B3 minus B2 B1. Okay, hopefully that's not very crooked. Is there a lag in the video, by the way?
No, not to my knowledge.
No. Okay, good. Yeah. Okay. 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 So now I have the contravariant piece of the F mu nu also. So let's calculate what is we want to find out what is d mu F mu nu. That's what we want to. So this will be something on the right hand side, right? I don't know what's it going to be, but some vector, because mu is gone, there will be something on the nu. So we want to find out what is that equal to. Okay. So let's begin with, so that is a 0th component. So let's put nu equal to 0. So when nu is equal to 0, I have an equation there. Oh, I cannot, oh, I forgot to move it. My bad. Okay. So I wrote the equation down, and so this is what I want to identify. D mu F mu nu is equal to something. I want to find out what that is, and let's first set nu equal to 0. Okay. So this will be, so nu equal to 0 sets it d mu F mu 0. That's what I'm finding out. But I know these quantities, so let me expand this. This is a index notation. So this is d0 f00 plus d, let me call it I fi0. Agreed? So that's a summation notation, right? 0. I run mu from 0 to 1, 2, 3. I is running from 1 to 3. Is that clear what I'm doing? This is 0, so that goes away immediately. And this is di. Di is gradient, right? So that's gradient. And fi0, it is superscript. So fi0, that is this quantity here, right? If you so if you so it is this piece in there, right? I is running and the next one is 0, so that's this piece in there. So if I were to get that, so this is minus 1 over c times ei, right? That's a vector. That's nothing but minus 1 over c di ai is del dotted with e. And why am I getting a negative sign? Am I supposed to get that? Yeah, apparently. Yeah. Okay. And there is a c. Is there a c? Yeah, maybe. Yeah. Okay. With me till now? Now we use Maxwell's equation because we want to write Maxwell's equation in this form. Del dot E is nothing but rho over epsilon naught, correct? So this is minus 1 over C times 1 over epsilon naught times charge density. Right. So that's what it is. So that's your zeroth component of whatever is on the right. Okay, so it seems like charge density is zeroth component of a vector. That's what it means. Before we reach to the full, let's do nu equal to I, like the space piece out of it, and let's see how that goes about. Right? Any questions until here? The motivation clear? What we are doing? Yeah. Okay. So let's. Okay. So same thing. Now we want to do with d mu f mu I. Right? That means the nu doesn't take any zeroth component, but mu will take. So this is d0 f0i plus dj fji. Right. This is nothing but time derivative, remember? So that's 1 over c d by dt. f0i, that's the top part of this tensor. If you, yeah, that's on the board. That's the top part of this. So that's a 1 over c e I. Time derivative of electric field is coming in. That seems to suggest that that's one of the Maxwell's equation that has the time derivative of the electric field. Del cross B might be. And FJI has a magnetic field in it, but we want to see the curl in here. So let's go back and manipulate this a little. So notice that so notice Fij was equal to dIaj minus dj ai, right? And we identified this with a vector which is magnetic field, right? It seems like there is a magnetic field there, but how we can see that is that epsilon I j k, remember your cross product can be written in terms of Lewis-Civita symbol, times bk. Remember, whenever this was 1, 2, this was the third component. Let me go back there. So when this is 1, 2 component, right, of the tensor. 1, 2 component of the tensor gives you the third component of the magnetic field. 2, 3 component, or this is 1, 3 component, gives you the second component. How should I write this? Maybe writing will help. So this is, we have F1, 2, F2 or F1, 3, and then I have F2, 3. Correct? So that's 0, and then there is F1, F1, no, F0, 1, right? 0, 2. Is that clear what I'm writing here? F1, 1, right? So that's F3, 3. Right? These are all zeros, right? That's your 4 components. This one is your magnetic field. So F1, 2 is nothing but it gives you B3, or this gives you B3. So the idea is that, oh, whenever this is 1, 2, this kind of picks it up, epsilon 1, 2, 3. That's the one that survives. If it is 1, 3, that gives you the negative sign also because it's 1, 3, 2. So that gives you the negative sign also. So this is an identity. Right? This is again based on observation that Fij can be written as in terms of Lewis-Civita symbol. That's your pk. Is that clear? Okay. If you allow me to do that, so then we have if we go back to this. This is nothing but plus dj. Since these are spatial components, whether it is upstairs, downstairs, doesn't matter. So this is j I k times b of k. With me, so I simply replaced this with a pattern that I saw, and this gives you 1 over c square times d by dt of electric field. Now, right, I there, and I can move my j and I, right? So it is minus of epsilon I j k times del j. It doesn't matter the space parts. I can make it upstairs, downstairs. So that's pk. That's a cross product, right? Cross product of the gradient and the magnetic field. So that's equal to 1 over c square d by dt of the electric field minus del cross b, and the whole thing is we are taking the ith component of this.
So how did it become minus when you went from the?
Because I switched the sign here. If I flip.
Oh, okay. I thought you just
moved
the gradient part and then it changed the sign.
Yeah, I changed the sign after.
Okay, cool. Yeah.
Okay. And that is what is that? Right. That's one of our Maxwell's equation. Remember? So let's look at which Maxwell's equation it is. So let me go back. Third board. we have del cross B is equal to d by dt of it is B over mu, right? Because we write it as del cross H. So this is B over mu naught. So epsilon times electric field plus J, charge density. That's your Maxwell's equation. Multiply by mu on all through. So we get del cross B is equal to mu naught epsilon naught E by dt plus mu naught times J. This equation shows up on the, so this is 1 over c square. So I can say that this is 1 over c square times dE by dt minus del cross B is equal to, I've taken this to the right, so I'll bring that to the left. So it's minus mu naught times J. Great. So going back to that board, this quantity here is minus mu naught times J. Okay. So what we have shown is putting it all together, collecting it at one place. So this is minus 1 over c. I know you guys cannot see this, but so I put it on top there. So I just copied this out there, and I'll erase this, and then I'll write d mu f mu I, right? So this is mu is equal to I, right? So that's a second piece, so that you have it all in one board space. That's equal to minus mu naught times J. And our goal is to find out what is this vector, correct? Is there anything similarity here? We would like to see this as some J there, right? So let's do something. Let me pull out, let me put a mu naught and put a mu naught there. Okay, so this is equal to minus 1 over c, or mu naught over c, and then there is 1 over mu naught epsilon naught times rho. That's nothing but c square times rho, correct? C square in the numerator. So this is the same as c square, so that's minus mu naught c rho. Agreed? So seems to suggest that if I both have mu naught in it, they both have negative sign. Let me pull that out as mu naught here. And whatever is left, let me call that as J nu, a 4 vector for current, where I identify, because Maxwell's equation has to be satisfied, J nu, the 4 current, the 0th component is C times rho, charge density, and the space part is just J. Okay. Because I minus mu naught is there, so this is the piece that survives, right? Okay. So in a sense, or this is nothing but Maxwell's equation. Can be printed on a t-shirt very well. That's the only thing. Has physics changed? No, it has not changed. Same equations, absolutely the same equations, but what's the advantage of all this? Now we know what goes with what. Remember, in Lorentz transformation, it's the length of a 4-vector that is invariant. Like if you want to observe two things in different labs, you want to compare things that can be easily is invariant among them, and we see that, oh, current and charge density is like space and time. They come together. Electric potential and vector potential, they come together. Right? These two come together. And electric and magnetic field come together, but in a much more complicated structure. In fact, it's a 2 second rank tensor, but still it can be printed on a board. Right? Now, for gravity, the complication is that is a 4th rank tensor. The gravitational field tensor that we construct, when you construct it, it comes out to be a 4th rank tensor. That's a complication, but we are not doing gravity. We will be working with this, and it's much more easier to deal with this. Next time we'll come and talk about how these things transform. Like if you move relative to each other, now electric field and magnetic field start changing, right? They will, but there is something invariant in this whole this. So we won't worry about how electric field changes, how magnetic field changes. They will change, but there are certain quantities that are invariant, and that's what is more interesting. Correct? Length changes, length contracts, time dilates, but there is speed of light remains the same, right? There is a proper acceleration that remains the same, right? So similarly here, there are constructions, combinations of electric and magnetic field that will not change, and that's what we'll identify next time. Okay. Or either we'll identify, depends on what I decide. I might just give it as they are as a proof, or I might prove it. Okay. Any comments, questions? I keep crossing the time always here. But yeah, thanks for listening. Yeah, hopefully this was useful. Yeah. Have you guys seen this before? In some form, at least in books or something?
A little bit. I've seen part of the field tensor before.
Okay. Okay. Yeah.
Yeah, I've seen it, but don't just, it's reminding the memory again.
Yeah. Again, nothing new as far as physics goes, right? Same equations. We just put the equations in a compact form. But it's more than just a notation in the sense that tensor notation and relativity has physics in there, that it tells you what goes with what. Like space and time goes together, has depth in it. Similarly, the electric field and magnetic field go as a tensor, has depth in it. Okay. Even though it's the same equations, but now we know that, oh, electric field, if you change electric field, magnetic field will change accordingly. That's, in that sense, there is physics in there, but nothing new, nothing changes. Like Newtonian physics changed because of relativity. Electrodynamics has not changed. It's just an insight that has changed. We have new insight for the equations. Okay, thank you.
Thank you.
Yeah. Okay.
Next time.